Finally, we came to the final point of our studying, the chaos and chaotic systems. And let's use this system as the example. This is third order differential equation and called Lorenz system, where sigma r and b some positive parameters. And let me read the text of one very good book written by Steven Strogatz, Nonlinear Dynamics and Chaos. Lorenz derived this three-dimensional system from a drastically simplified model of convection rolls in the atmosphere. Lorenz discovered that this simple-looking deterministic system could have extremely erratic dynamics. Over a wide range of parameters, the solutions oscillate irregularly, never exactly repeating, but always remaining in a bounded region of phase space. When he plotted the trajectories in 3 dimensions, he discovered that they settled onto a complicated set, now called strange attractor. Unlike stable fixed points and limit cycles, the strange attractor is not a point or a curve or even a surface, it is a fractal, with fractional dimension between 2 and 3. Let me repeat some important points. Here we have the parameters that can be changed, and we are talking about the range of parameters. Solutions of this system oscillate irregularly. They never repeat, but at the same time, they always remain in a bounded region. And actually, this complicated set is called a strange attractor because it is not like a stable fixed point and its phase portrait, and this is not like a limit cycle, and actually this is not a point or a curve or even a surface. This is a fractal, and dimension of this fractal is between 2 and 3. Let's look at the simulation results of this system with the following values of parameters and initial conditions. Our 3D graph for the variable x, y, and z is shown in this diagram. If we want to see the variables separately, x versus time, y versus time, and z versus time, then we have the following diagrams. And again, we see something repeating, something bounded in a region, and something oscillating but not regularly. If we slightly change the initial conditions, for example, here we have y of 0 equals -2, then we can also get the simulation graphs, 3D graph and the graphs x versus t, y versus t, and z versus t, and we see very similar behavior. We have a bounded region again, we have irregular oscillations, we have repeatings, and so on. And we can compare both cases with different initial conditions. We can look at these 3D graphs here, and we see the same what we listed previously. Irregular oscillations, repeatings, remaining in a bound region, so we can see the chaotic behavior. Now let me comment on the fractal features in chaotic systems. Let's return back to the simulation results with initial conditions, and let's take just one variable, for example variable z versus time, Let me draw the following. Let me draw the following frames. So if we look at the frames, we can see we have some repeatings already. And actually, if we take any of these frames and do the same but inside of the frame, we will have something similar. So you see, I also use trapeziums for drawing the purple frames. And actually, if we take the interval, for example, between 100 and 150, so if we take this region and zoom it in, then we can see everything in more details. So we can see here we have again such trapeziums, right? So we have the fractals here, and this is how chaotic behavior looks like.